Today I'm very happy to have with me Dr. Sakyasingha Dasgupta, founder and CEO of EdgeCortix, which is an innovative edge AI company that's working to transform the way we do inference at the edge in a power efficient and certainly a cost efficient way. Now I should mention Sakya is an experienced executive and also inventor, holder of 20 patents. And he was before founding EdgeCortix, he had a wide range of roles, including as a research scientist in robotics at IBM, and also in a series of startups. But at EdgeCortix, I think that he's doing remarkable work now, and has basically, I think, already had a significant impact, I think, in certainly the tech ecosystem in Asia. And just recently, EdgeCortix secured a $20 million round, including investments with SBI and also Renesas. So without further ado, I'd like to hand over the presentation to Sakya. We'll have 30 minutes and then we'll follow that with a Q&A session. So thank you. Welcome, Sakya.
Thanks, Damian. Thanks for having me and the really kind introduction that you've given us. So let me try sharing my screen here. Hopefully that should be coming up shortly. Hopefully that's visible for everybody.
Yes, great. Can see it perfectly.
So it's a pleasure to be here on the Macquarie's AI event, and I'm looking forward to walk you through what we are doing as still a relatively young company. As EdgeCortix, we are headquartered and based out of Japan, which by itself is quite unique at the intersection of AI and semiconductors. So I'm hoping to walk you through our journey in the process of building both silicon and software focused on the edge AI market. Okay, so I would say, as the title suggests, what I would like to focus on is our journey of building what we call best-in-class, really energy efficient, power efficient, sustainable AI processes, which also aims to bridge the apparent gap that exists today in the ecosystem around software and hardware. And we take a very unique software-first approach to build such AI silicon. We'll also look at what I would like to call 5 fundamental challenges that we are solving as a company, which is also the 5 fundamental challenges that exist, in our opinion, within this entire AI semiconductor ecosystem that we need to be able to solve in order to create a lot more power-efficient systems and really cater to the requirements of our customers, whether that's an enterprise customer or anybody else. It'll be a very tall order to answer all of those challenges, but I'll walk you through our journey in that process and how our business is catering towards that. So without further ado, let's jump into it. If you think about AI today, and as this slide kind of depicts, we're really living in extraordinary times where we can build these AI systems that can work beyond or at sometimes at the same level as human capabilities in many cases. And really, it's technologies like generative AI, large language models in the last 12 months or so has created this tremendous demand that although existed over the last 50 years that AI has existed in 50, 60 years, we have never really seen these tremendous demand for AI systems since the last 12 months or so. And that is also creating a very different environment within which these AI applications, systems are also changing the way we build silicon, the way we design chips in order to cater to the requirements of those AI applications. And that's what I want to focus on today. While there is this explosive growth of AI, there are also some fundamental challenges. And as I said, we will focus on those challenges. But before that, let me just walk you through how we as a company, through our product portfolio across Meta, which is a software product, DNA or Dynamic Neural Accelerator, which is a new patented IP or technology that we have brought to market, as well as our AI silicon called Sakura. Across these product portfolios, how we are solving certain use cases, I want to showcase that with a quick video that will illustrate that, and then we'll jump on to the challenges and how we are solving those challenges. Hopefully the sound of the video is coming across.
Might not be at the moment. Let's see. Okay, this now, I think. The audio is not coming through, I believe, but we can see it loud. I see it perfectly.
These are different use case scenarios under which our customers are already using our products today across the software and the hardware portfolio. Whether that's smart city, as you see here, or innovative traffic management systems using the power of AI, or thermal cameras under automotive or similar scenarios where AI is being used to add more information than what's possible natively from the sensor itself. Even across applications like generative AI, where you have different modalities like image, video, data, or text, all working in hand together. All right. Hopefully that gives you a glimpse of the different use case scenarios that we are solving today with our products. With that, let me jump into the key challenges that exist today in this AI semiconductor ecosystem and how we are solving them. Challenge number one, I call this software 1.0 versus software 2.0. If you look at the left-hand side, that's really what we know as software today. You're familiar with probably explicitly written lines of code, as you see here, perhaps familiar to some of you, perhaps not so familiar to some of you. But the whole idea is that it's written code, whether that's C++, Python, standard computations based on specific input data, or in other words, programmers are explicitly mapping some input data to some kind of written code. That's the age-old paradigm, which is very different from AI. On the right-hand side, that's what we understand by AI today. A neural network, or we also call this software 2.0. It's a completely different paradigm of programming, where if you see this example, that's a modern transformer network. That's really the key technology that's driving ChatGPT or all these types of applications that you would have heard about recently. There is no explicitly written code typically, but rather the network is defined in a manner that it learns or discovers the code from its computation. Typically, by learning a representation from what we call training data, so examples of what it's supposed to learn, and then discovers that through a network architecture that essentially is a graphical flow of information. And this paradigm of software 2.0, which is basically a graphical representation, typically no explicitly written code where you're defining every single parameter, you're kind of learning the inherent representations from data. It also requires that if you're creating silicon for that kind of a software, you need to think what are the idiosyncrasies that exist within that software to be able to solve that. And that very different paradigm is one of the first fundamental challenges we are solving. The second challenge really is not very unknown. Perhaps earlier today, you might have heard about that from a semiconductor perspective. We call this Moore's law. And if you think about Moore's law as this graph depicts, on your x-axis, that's time. And on y-axis, that's basically just a logarithmic scale that's showing progress. The white curve that you see here, that's the traditional curve of what we call Dennard scaling. So that's essentially indicates what is the multi-core processing utility over the years. And in 2005, 2006, as an industry, we have stopped scaling in terms of adding more cores to our processors. Even if you add more cores, you're not going to really get enough value out of it. The green curve really depicts what we have called strictly the Moore's law, where you would expect to have essentially a 2x every year increase in transistor density per millimeter square per area of the chip. And as we can see from this curve, it really has stopped scaling. So the strictest definition, Moore's law has ended. However, it is not all that bad. There is still a more optimistic view that we can take from a Moore's law perspective. So although we are not seeing benefit from pure transistor scaling, there is still this optimistic view that we can take from system scaling. And that's depicted in this yellow curve, so to speak, as well as the projection across the orange curve. By using combinations of what we call chiplets, material properties, as well as other types of system scaling properties, we can really push forward the previous generation Moore's law and still continue scaling, perhaps at a rate of 3x every 2 years. And this phase, in our opinion, is going to be largely dominated by new discoveries, new material properties in 2D or 3D packaging technologies, as well as architectural innovations, as well as combinations at a system level in the form of chiplets and system in packages. But the challenge still remains for us to be able to embrace all of that in order to continue innovating in the AI space. Now, if you look at challenge number 3, the picture becomes even more starker. In your gray curve here, that's the traditional Moore's law. So your x-axis is still time, y-axis is the amount of compute required in the AI domain, and it's a log scale. So every curve here is an exponential curve. And if you compare the blue and the red curves compared to the Moore's law curve, that's where the problem is. Even if Moore's law existed today and continued to grow at the historic rate of 2x every year, we would not be able to catch up to the order of magnitude growth required for traditional computer models like computer vision, natural language processing, speech depicted by the blue curve, or the recent explosion that you're seeing in terms of transformers, which is going at 2 orders of magnitude, more than 100x faster than Moore's law. As a result, in order for us as an industry, as a company, to create technology that can catch up to all that compute requirement for AI, we really need to rethink and innovate both architecturally as well as software. So that's the third challenge we are solving as a company. The fourth challenge is what I call memory bottleneck. If you now look at, again, your x-axis, you have time. On your y-axis, you have performance. If you compare the green curve, that's really the growth of memory year on year compared to CPU, which is your traditional general purpose compute, or deep learning processors, which is basically AI-focused processors. You can see that once again, the gap is enormous. While compute is continuing to grow, the amount of growth in the memory side is not equivalent. So there is clearly a big mismatch between our memory performance growth versus the compute performance growth. And that's another fundamental challenge we need to be able to solve. And one way of doing that is, again, architectural innovations by bringing processing or computations much more closer to memory. So that's the fourth challenge we are solving as a company in order to cater to all the expensive memory requirements for AI models. Just to give you an example, the generative AI models, large language models, these are very, very memory sensitive models or memory heavy models. It requires a large amount of memory to store all those billions of parameters of these models. As a result, if you're not able to process all that information at the same bandwidth as your compute, that will start to become the major bottleneck. And that finally brings me to challenge number 5. That's the fundamental challenge that we are trying to solve. The mismatch between performance and efficiency. You not only need a very high amount of performance, as clearly depicted by those curves we have seen for AI, you also need to ensure that it's power efficient and it's sustainable, it's greener. Unfortunately, if you look at the data on the left-hand side, if you can see my cursor here, it's not a very optimistic view of the world today. The top data shows the environmental impact of just the standard models like GPT-3, which is probably the model that you've heard from companies like OpenAI. The amount of power consumption and carbon emission required to train those models is just unsustainable. In fact, the recent statistics is a single training day of that kind of a model, GPT-4, requires up to 700,000 people's equivalent of power consumption. Unsustainable. If you look at the bottom data, that's a few years old, even before ChatGPT existed. So clearly the amount of carbon emission here of a single model is equivalent to the lifetime of 4 cars, automobiles. Clearly unsustainable. So how do we actually cater to the compute requirements of AI and yet create a very sustainable, environmentally friendly, and power efficient solution that gives much better performance per dollar advantages to our customers. In order to do that, I would like to kind of talk about this difference between performance versus power. So imagine that your performance is on the x-axis, and imagine power of all of these systems are represented by the y-axis. All systems today in the industry can easily be classified across any of these four quadrants, where on the top left quadrant, you would have something like a zone of uselessness, so to speak. It's a little bit harsh, but really think about it. If you have a compute platform that has very little performance, but very high power, there's not much use of that, especially in the AI context. Most data centers today, like GPUs and other processors, are really a lot of performance, but they also require tremendous amount of power consumption. And then you have at the other end of the spectrum, very, very low compute requirement, low performance, lower power, what we call sensors or edge endpoints. They are suitable for certain applications, but clearly cannot scale from the edge all the way to the data center. We as a company, we are focusing on this bottom right quadrant that I call zone of high efficiency, where you can have the right balance between high performance, but at a lower power. And we do this by concentrating on this curve that you see here, shown in blue or maroon, however you see it. This curve is not static. We can dynamically move this curve either vertically or horizontally. And by innovations across the architecture and the software side, we can now build AI silicon to be significantly more performance as well as power efficient. That's the fundamental challenge we are solving as a company. So how are we actually doing this? If you take a look at general purpose processor landscape, it is not very hard to plot their utility across two primary dimensions. So once again, I'm drawing a dimension in x-axis in terms of software flexibility, which basically means software 1.0. That's your general purpose software, how easy it is, how general purpose is the software. And on your y-axis, you have efficiency. That means how much performance per watt can I extract from the processor? And really, CPUs and GPUs are the most general purpose. You have a lot of software flexibility, but you're trading that off for the efficiency. In order to extract breakthrough, really 10x or more efficiency, performance per watt advantage, we are concentrating on this middle ground where we are building what we would call software 2.0 defined architectures that brings this AI acceleration at orders of magnitude better performance per watt. Where by concentrating on software 2.0 or AI domain, we can now create software that is tailored to AI, but create silicon that is significantly more efficient. That's the core mission for us as a company, where we are building software-defined AI architectures and bringing solutions to enterprise or other customers where we can achieve cloud-level AI performance with orders of magnitude better energy efficiency, so much more better power efficiency, significantly faster processing, and as a byproduct, much more lower total cost of operation across the lifetime of deploying that solution. Second, rather than pure data center, we can bring higher performance AI processing capabilities directly to the site of this massive data creation while being significantly lower power. And if you look at this picture, where is all that data? So data is really the new oil that is driving all these AI applications and models. And as it turns out, most of that data, the highest volume of our data is actually sitting at the enterprise edge or the consumer edge. So if you get closer to the site of the data creation, where 75% of all enterprise generated data is going to be either created or processed directly in the edge within the next couple of years. And by bringing computation capabilities directly to the edge, we can now reduce all that expensive data movement required to go from the edge to the cloud, which as a byproduct is also a lot more privacy and sensitive as well as more secure. And that's kind of the second method by which we are solving that challenge, by bringing compute directly to the edge. The third piece that I want to highlight is the entire principle that we have changed in terms of designing and bringing solutions to market, where our key design principles as a company is creating very, very modular, scalable architectures whether that's software or hardware, that can very easily scale from smaller form factor to larger form factors. We are taking a very software-first approach that has allowed us to work with even leading companies like Renaissance and others, where our solution not only works for our own purposes, but it's able to cater to the requirements of third-party silicon companies and bring value to the ecosystem. Third is silicon-proven IP. By bringing our IP and proving that with silicon, we are able to ensure that we are making very robust solutions in the market. Third, we have been partnering with leading companies, and I'll talk about that a little bit later, by building an ecosystem approach using state-of-the-art EDA, electronic design and automation tools. We can accelerate the development speed. And finally, this is very counterintuitive to the semiconductor industry, smaller teams. Historically, semiconductor industry used to require hundreds of teams at the lowest end, perhaps even thousands of teams to develop and bring a solution to market. We are now seeing that by taking this approach of scalable design, where IP can be used like building blocks, we're almost moving to a Walmart type model where you can walk into Walmart today and buy different products. We are envisioning an environment where you have standard proven IPs and perhaps even processes like chiplets already ready, where you can pick those up and create them as building blocks to create scalable designs. And that can be achieved by smaller teams. In fact, the first silicon, when we brought that to market, we used a design team that was just 10 people. And that has a tremendous impact on the way we bring the solutions to market. So on the right-hand side, some of the key aspects is flexibility. We are creating solutions that can rapidly deal with the changing landscape of AI. As we all know, AI is changing rapidly. So you don't want a solution that works only for one type of AI application and not for the other. The second is it's very, very high performance, but at low latency. If you think about the edge, most devices require real-time performance, whether that's your smartphone or even a car. If the car was to stop every few instances and then take a decision, it's going to be very, very difficult. So it has to be extremely real-time. Third, as we discussed, low power consumption. Typically, the edge is constrained by what we call SWAP, size, weight, and power. As a result, you need to be very, very power sensitive to bring that same performance. And then finally, it's a little bit of technical term, parallel pattern data flow, but the key idea is design for the intricate properties of software 2.0, which is basically a data graph. We are doing this today through an innovative architecture. I won't go into all the technical details, but highlight some of the key building blocks. We call this modular and scalable design, dynamic neural accelerator that was patented and invented by EdgeCortix, completely in Japan. The first piece is that it's a fully configurable AI processor, almost like a Lego-like building block where you can take very small form factor designs and then scale it up. So you can go from the edge to the data center in the future. We support what we call mixed precision. So you can mix and match different types of calculation parameters so that you can preserve accuracy, which is very, very important. You would not want to sacrifice accuracy of your AI application for performance. We have innovation around memory and compute, as I talked about, to deal with the memory bottleneck. We call this distributed memory. And then finally, runtime reconfigurability. I just want to highlight this with an example. Think about a highway that connects different parts of a city. Let's say in Japan, Shibuya, Shinagawa are all connected by a highway. Now, just like the highway makes it a lot more efficient to travel across the city landscape, we have such a highway, a data path that connects all our compute engines. Now, if we can use software and decide how to route information such that different parts of the city or different parts of the silicon can work as a complete unit when it is required by the application. So that can trade off computation versus power. And when you don't require it to work, you can shut down the highway. You can switch off the different parts of the city, saving power. And that dynamic balancing of power and performance gives us the unique ability to make our silicon future-proof, as well as get significantly higher performance per watt advantage compared to others. With this, we are bringing to market what we are calling silicon solution that is designed for efficient generative AI at the edge. And finally, of course, I haven't forgotten software. I won't go into the technical details, but the software that we have designed, it works with all standard open source frameworks, as you see on the left-hand side. As a result, we embrace open source, make it a lot more scalable and applicable across the ecosystem. And then you can deploy that across heterogeneous mixtures of processors. For example, mix and match ARM, x86, or RISC-V, together with our proprietary technology in the form of DNA. As a result, we are able to even provide that same benefit of our software Mera to third-party silicon companies like Renaissance and others in order to help unify the ecosystem of products that comes from many other companies. So what did that give us? That approach that I just talked about has enabled us to bring to market our first generation product, which is currently with customers, called Sakura One, is our first generation Sakura device, which is the best in class edge AI processor, where it allows us to go from very high performance. We're talking about trillions of operations per second at the same level, if not more, compared to GPUs in the same space, while requiring just less than 10 watts of power consumption. That gives us enormous scalability, future-proofing it so that it works across vision applications that you have today, across smart city or camera applications that we saw previously, as well as generative AI, efficient language models, and then also preserve the accuracy. That allows us as a company to be able to scale from single chip to devices or cards that are replacements or complementary to GPUs in some cases, and then full compute boxes. We bring that to market with a complete platform. We call this the Edge AI platform that combines the three product lines, Mera being our software that works across all standard machine learning open source frameworks, DNA being our IP, that we can make it work with other types of hardware. Here we partner with some leading companies like Intel or AMD on the FPGA side, as well as companies like Renaissance on their MPU and microcontroller side, together with our Mera software. And then finally, the Sakura silicon solution gives us the unique ability to provide all of those benefits directly in a silicon or a semiconductor. That enables our customers to reduce the AI deployment time from multiple months, in the worst case, to just a few days. So how do we actually perform compared to some of our competitors? So I just wanted to highlight one aspect here. If you look at the left-hand side, this compares our first generation chip, Sakura One, which was a TSMC 12 nanometer product, around 40 TOPS of compute. It is 4 times smaller in size compared to an equivalent GPU in the market, which is also in the same process node, 12 nanometers. The 4 times smaller gives us a significant advantage in terms of our cost. As you would know that in silicon industry, area is directly proportional to the cost when you're in the same process node. So as a result, we are more than 5 times better in terms of performance per TOPS, so our compute efficiency. We are 16 times better in this example in terms of our power efficiency, performance per watt. And the 4 times smaller size gives us significantly better advantage, typically 5x, compared to this example in terms of performance per dollar, which allows us to, of course, price our products competitively while having a significantly better gross profit margin. Even when you compare our products to latest generations, so let's say our 12 nanometer product compared to a 7 nanometer GPU, some of the latest GPUs, we are still able to preserve more than 7 times in terms of power efficiency and still be more than 4 times faster. This is on one particular use case examples. There are certain customer models where this gap on our advantage is even more higher. To summarize in the next few slides, I just want to talk about this ecosystem that we are building. It's not just about us as one company. Really, at the AI and the semiconductor side, we need a robust ecosystem. As a company, if you were to classify us, we are a fabless semiconductor company within the semiconductor value chain. But over the last few years, as a company, we've been building a strong partner ecosystem. As I mentioned here, working with leaders like TSMC, amongst others. That gives us the ability to create a strong and reliable path to mass production. And with that, we are able to bring all of these solutions to our customers across the edge landscape. This has also allowed us to rapidly scale across our technology and product roadmap, as just showcased here. Since 2019, we have rapidly been bringing to market an industry-first heterogeneous compiler technology that can work across many types of hardware. From 2020 onwards, we've been partnering with leading FPGA and third-party companies like Renaissance, so that that same value of our software can be provided with other leading companies. And then we have brought our own silicon product to market. And as we are scaling across, now we are making a bet towards chiplets so that we can now scale beyond just the single monolithic dies and embrace the system scaling aspects of Moore's law, as I talked about. And of course, all of this would not have been possible without a very strong team. So we have a very distributed workforce across Japan, US, and now we are also starting a new center in India. That really enables us to bring all of the solutions to our customers. With that, I would like to thank you for your time, and I'm hoping to take some questions and perhaps share a little further thoughts about how we are bringing the solutions to market.
All right. Thank you very much, Sakya. That was, I think, very informative. And I think, yeah, many of you who have spoken about or have talked about semiconductors with me, I think understands how important power efficiency, memory bandwidth is. Maybe I think just to kick off a little bit, clearly I think you're founded in 2019. Could you talk or give a flavor of like the kind of commercial traction you're getting with AGI? We've all heard about the tons of GPU that NVIDIA is selling, and the AMD has now launched their version. How is it translating to the business environment for EdgeCortix?
Sure. Thanks for that question. I think it's a very relevant and apt question. So as I talked about in the use case scenarios, I think the edge market in itself is quite fragmented. What we are seeing is that there are different types of applications that customer is looking for. Where we are finding the most resonance today is across, I would say, 3 or 4 different verticals. One being on the commercial sector with smart cities, manufacturing. So for example, applications like predictive maintenance, retail AI, where customers are essentially looking to deploy a solution with the combinations of different types of cameras and on-prem devices. Those are all important areas where you need a real-time solution. So that we are seeing some traction there. And then finally, in the area of, which is the intersection of AI and 5G, one of the works that are unique to us is that our IP is not just applicable to AI, but we are able to use that IP in a little bit modified form for accelerating 5G workloads. And that's an area where we showcased in the first quarter of this year, along with the leading telecom company in Japan, that we are able to accelerate those encoding, decoding workloads of 5G more than 10 times compared to some of the status quo solutions in the market. So that's another area where we are seeing high growth on the commercial front. Another area is the robotics and ADAS aftermarket. So where you have combinations of LiDAR, radar, different types of sensors, and you saw some examples during the use case videos. And then also in the robotics segment, where there are either unmanned, in some cases, aerial vehicles, ground vehicles, undersea vehicles, which are all constrained environments, which requires very high power efficiency, but real-time performance. That's another area where we are essentially seeing traction building up. And finally, I would say the defense and aerospace industry. That's another area where we are seeing some early wins. In fact, I'll talk about one such aerospace customer. I will not be able to share the name, but one of the leading aerospace companies globally, top 5, we've been working with them, going through their evaluations process, and some of the results that they obtained with the silicon has even surprised us. For example, for a scenario which requires decision-making capabilities on board a commercial jet, where you can use AI applications in order to run all the different signal processing models, they have been able to successfully compare our devices across standard GPUs, CPUs, as well as FPGA solution that uses our IP. And we were very surprised to see that on those particular very domain-specific applications, we were as efficient as more than 500x, so more than 2 orders of magnitude compared to a GPU, which we were ourselves surprised by that data. So there are some such use case scenarios where the gap of our advantage is even higher compared to what I've showed today. So these are some markets where we are seeing some early traction. I think the market is still developing. We are expecting that our unique ability to combine different types of hardware platforms together from a software perspective will give us a lot more advantage. One of the key aspects is, if you think about a solution in the edge market today, there are already existing hardware platforms. Most likely a customer is already using ARM or RISC-V, for example, or maybe x86. ARM and x86 is very prevalent. No customer wants to completely change their infrastructure. They want to keep their existing infrastructure, but add more AI value. And that's a software challenge. can you have a software that can easily work with existing systems rather than look at replacing that? That's what we try to solve with this heterogeneous platform, where you can mix and match different types of hardware. So the barrier of entry is lower, and that's where we are seeing more easier market penetration, and we expect that to continue growing as we start working with more and more customers.
I think this is an interesting slide. I'll come back and go back to applications in a moment. It strikes me that one of the interesting and unique aspects of your business is that you started actually with the software. So you actually most cases I've seen is, of course, we have, what I call it a big iron approach. So you have a ton of GPU. It sits there. We spend lots of money, and then we essentially like stuff all the data in and train your models that way. But what you're saying is that you take the models and you run it through your software, and you say I can fit that into any hardware you throw at it. And this, to me, strikes me as seems a much more efficient and sensible way. Why don't we do this more in the industry?
Yeah, that's a great question. To be honest, that was the first thing that we looked at. So when I was starting the company, kind of the first aspect was, see, it's not about the silicon. And unfortunately, even though we are building our own silicon, the silicon industry has always been hardware first, where you bring a silicon to market and then software almost becomes an afterthought, where you then start to go and understand the pain point of the customer. There have been some differences. The reason why GPUs are doing so well, it's not so much because of the hardware. We have clearly identified that the hardware is not so suitable for AI. But the software ecosystem that they created along their GPUs has worked very well. But the challenge there is that you are either within the GPU world or you're not. So you have to embrace that. So the first thing we wanted to solve, can we create a software that has the same properties of working as well with our own hardware, in a similar manner can also embrace the qualities of other hardware, so that customers can mix and match different types of hardware. And we are now seeing traction. So there are many companies who are starting to speak the same language of software first approach. We started that. So we are flattered by the fact that there are other companies who are embracing similar verbiage and kind of talk about that same aspect. And we are seeing that as the market grows, it will be very important to mix and match that. I'll give you another example. Take the example of one of our strategic partners, like Renaissance. In case of Renaissance, they have these really great products around their microcontrollers and microprocessors that solves the pain point of customers around the edge side. And where we have been seeing strong partnership between our companies on the strategic collaboration side is by combining the power of our Mera software together with some of their existing products. We are able to enhance the value proposition to the customer, where now they are not limited within just one tool chain that can work with, let's say, one type of model or one type of framework. The possibility becomes enormous. So they can mix and match the power of ARM with custom processors like EdgeCortix or Renaissance. They can mix and match the power of different types of machine learning frameworks, PyTorch, TensorFlow, ONNX. And that means you can now bring the widespread growth that is happening in the open source world into the hands of a user that's using that hardware. And that is truly energizing for us.
It sounds like maybe the analogy I put out to everyone is kind of like, if you wanted to stick an engine to drive something, you realize it's not powerful enough. Now I can essentially tack on a supercharger or a turbocharger to it, specifically for the AI. And it basically gets the job done. And it strikes me, especially when earlier you mentioned the applications. I can see, imagine if you're flying on the plane for all listeners. Imagine like you wanted to get AI done, but you can't connect from an airplane to some cloud-based data center somewhere because you're flying in the air. It seems to me that universe of applications and devices that's disconnected, from essentially the main network. It must be very large. I think it's almost like I would say, up to the imagination to figure out like what kind of use cases you can apply.
Absolutely. And I could not have said it better. I think turbocharging or supercharging is the right adjective, to describe what we are essentially doing here and what the industry is trying to do. We call this accelerators precisely because of that reason that, you don't need to add AI capabilities into everything. But what you're doing is you're seamlessly adding an additional tool, so to speak, that you can offload all the AI processing to. And the software does the heavy lifting of removing friction that may come typically when you're adding any third-party tool into the mixture. That's what our software solves. It solves the friction of going across two different platforms. And then our hardware solves the problem of giving a lot more performance and efficiency. And I'll give you another example, where even if you're connected by network, you might not want to always process across the network. So let's take the example where, like a car. Now, today, with most cars, the internal car infotainment systems, you're able to converse with the car, but it's very, very limited. It's having a communication where you're essentially telling it to do certain things, but there's not a lot of feedback. Visual information is not coming back to the car. And that is privacy concerns. So if you now have a camera that's looking at a person inside the cockpit of the car, or for that matter, an aeroplane, you don't necessarily want to send all that data to the cloud because of privacy, and notwithstanding the fact that it is going to be high bandwidth requirement. To be able to process that, as well as the ability to process multiple modalities like vision, image, video, very, very quickly, within all the sensor ecosystem of the car, that's a game changer. And that's what we are trying to do with what we are calling the generative AI chip products within low power, 10 watts power consumption, but very, very application-specific generative AI models that can directly run on the platform itself.
It sounds very exciting. And I certainly want to give a chance to those who are dialed into the call to have your questions. Now, I forgot to mention this at the beginning. If you have any questions, please use the chat box. Put in the question, I'll curate it, and I'll refer it to Sakya. Any question you do about the technology, the platform, use cases. In fact, I'm going to continue on the topic of use cases and say, this sounds like something that would actually help proliferate, in fact, computation, because it's almost the first thing on the software, the removal of friction. It almost seems like there can be use cases that haven't been tapped yet, if only you could actually make it easier to deploy. And so what you're saying is that the software actually makes it easier and more likely to deploy this, in the models you want, the frameworks that you want, and therefore you can go to Renesas or anyone else, NXP or anyone else, and say like, now I have this tool, I can deploy, for instance, an industrial machine or inside an edge sensor, for instance. I could basically monitor cow farts, for instance, if I wanted to. But things that couldn't be done before can now be enabled with your product. That would be probably your idea.
That's exactly right. That's the vision. And I'll qualify with the fact that, we have not complete, everything is not yet done. There is definitely a lot more work to do. But the building blocks of what we have brought to market exactly contains that. The idea is, super heterogeneity. For example, in many customer cases, I'll give you another example. So let's say signal processing. And we work with some customers who are running signal processing application where they're using AI to identify where certain signals are appearing from and whether that signal is probably a good signal, a known signal, or a bad signal. It is not very different than doing object detection. So you're essentially looking at the image spectrum of that signal and identifying whether you know that pattern or you don't know that pattern. Because it's a signal, you actually need to do that as fast as 1 millisecond in many cases. That's extremely high sensitivity, very fast. It has to happen on the device itself. Now, the AI piece can run on our processor, but there are certain typical signal processing algorithms that are better suited actually for a GPU or maybe a DSP. By matching those different processors within our software platform, we enable the customer to be able to do that. They don't need to make the choice of having to completely move to an AI processor where you're either choosing that processor or you're choosing your existing system. Now you can stick with your application where you had a CPU or a DSP and you plugged in an AI processor into it, and the software manages the ecosystem. Or you can have an application where there's a CPU, a GPU. The GPU does the non-AI workload, which it is very good at, and then all the AI processing gets offloaded to our processors. Those are ways in which we are seeing this platform growing in the future.
It reminds me of my kids telling me about dinosaurs and how they had multiple brains, because the brain was so far away from the tail that they needed a little brain at the base of the tail to handle the tail. So this is essentially distributed intelligence. You just need to find ways to partition the workload in the appropriate way. There's a question from the audience. I'm going to read this out. So curious to understand, seems to me that any hardware player allow EdgeCortix to use the software will over time lose value of their own product. I'm not. How would EdgeCortix work to fix that? So, so I think the idea would be that eventually, as someone like Renaissance who works with you will actually lose control over their own ecosystem to you. That means you capture more and more of the value. How do you address that? Is this an issue, and how would you address that?
That's a great question. And I would say it's actually the contrary. So by embracing our software in the ecosystem, we are actually enabling them to democratize the solution to a lot more wider customers than they are singularly able to do that. So the value proposition is that, imagine this software, it's basically a platform where they're able to now add more either functional advantages or performance advantages than what is singularly possible on the platform itself. And they as a company can now concentrate on what they are good at, building the silicon, building the IP, their own tool chain, rather than having to worry about how does the ecosystem platform develop. And I think that's kind of the key aspect of not losing value, but rather the value of the product ecosystem growing further. They will be able to penetrate a lot more customers than what they were able to singularly before. Equivalently, going across hardware players, different hardware players bring different capabilities. So as I gave you the example, CPU, GPU with us, or a CPU, DSP and us. Since today, there is no such singular platform that existed that could mix and match. Customers were having to choose to go to one or the other. The cost was higher, as well as the companies who were creating DSP were, for example, having to do everything themselves, which is tough. It's very tough to do software and hardware and all of those pieces all together. By taking out that pain point of working across multiple hardware platforms, we are enabling multiple hardware players to work together, which they would have found it difficult to work previously. So I think that's the additional aspect of, we see the value proposition as well as the value of the product increasing over time rather than decreasing.
Got it.
Hope that answers the question.
No, I think it does. That's great. And if there's a follow-on, please feel free to keep throwing the questions into the text box. I'm going to touch back on EdgeCortix's obviously business development in 2024. We're coming to the year end. It's been an exciting year for EC. You obviously have Sakura, your 12 nanometer based chip is coming out pretty soon. It's
already in the market.
It's in the market. Okay. That's great. So what plans for 2024? Are you is suddenly you have a partnership with Renaissance, you have the chip out in the market, sure. And you've just raised more money. And what within the limits of what you can say, what are the key priorities of building the business in 2024?
Sure. No, absolutely. So, of course, there are certain things that I can say, and some, it would be difficult to share all the information, but they are, all, it's a great time for us. One of the fundamental things is, we have already validated our silicon, and what we are doing next year is that we now have a good pipeline of customers that with whom we are scaling, as I mentioned, across whether it's aerospace, commercial versus defense, as well as smart city, smart manufacturing, retail, AI type applications, and we are seeing growth there. So 2024, we have what we are calling a second generation chip, which is also in the TSMC 12 nanometer, but caters to what we call generative AI at the edge. We will be bringing that to market in full mass production in the early, to mid half of next year. That will be able to solve the current generation language models under what we call efficient language models within a 10-watt spectrum to further democratize that to customers. Today, there is no solution as far as we are aware of that can do that. And I think that we are seeing that the industry will grow even further on the generative AI space by bringing much more domain-specific generative AI models rather than the general purpose models that you're seeing today, like ChatGPT and others, to the hands of various types of customers. And we will solve that pain point with the second generation chip that we are bringing to market. And part of the raise actually enables us to do that mass production. Along with that, we are also, focusing a lot more on continued software growth. As I said, today the software's building block pieces are there. We are able to mix and match different types of hardware, but we are adding a lot more capabilities on that. So we will talk a little bit more on that. We are also looking at, enabling the customers even more in terms of easier ability. So today, some of the customer personas for us are typical machine learning engineers. We are trying to further democratize our software solutions such that anybody, even without having to understand or program software, without any coding knowledge, should be able to use our software to play with its capabilities and try out different types of hardware platforms together. So that's another feature that you would expect to come to the market, driven by some of our customer demand. And then finally, as we go beyond 2024 into the future, we are also making a bet on the chiplet ecosystem. It's a little bit early for us to share all that information, but I will say that there's a lot more development on taking our current generation product, which is already silicon proven, and we are looking at a little bit more advanced technologies, but allows us to scale with a chiplet product that can combine various types of other IO or other types of chiplets together and create even more scalable, higher performance product without sacrificing our power efficiency. Those are some important developments that we are seeing, and then we'll continue to grow our team. As I mentioned, this year we brought to the team Sudhakar Kale, who just joined us as a new VP of Silicon Engineering. Sudhakar, he is 30 plus years of experience in the silicon industry. Previously led teams like AMD's center in India, and then most recently, before joining us, he was part of Samsung. Under his leadership, we are kickstarting a team in India, an India Design Center, that will allow us to further accelerate the development in APAC region, with, of course, Japan continuing to be the key center.
Well, that's fantastic. I think the chiplet thing in particular, I'm certainly interested in this one. But before I go there, I guess one question that must be on the mind of at least some observers is, how did you get this far with as few resources and people as you have? When on the other side you have like this juggernaut called NVIDIA with tens of thousands of people. In fact, they might have more than that now, and all the resources in the world. And isn't this a space that they might eventually like catch on to and challenge you?
Yeah, I mean, so I think it's a tough question in general, and we get that quite often. I think this ecosystem that I've been mentioning is very important. It's singularly one company cannot do everything. So when we started, we had very clear ideas, and that idea was, as I mentioned in the beginning, the software challenge. By taking that software-centric approach, we already knew that we want to first focus on creating a platform that can bring multiple types of hardware together. That meant that even before we went the silicon to the market, our prospective customers were able to validate and try out our software with existing hardware. That gave us early win, notwithstanding the fact that it enabled us to generate revenue that you typically don't see with many silicon companies right in the beginning. The second aspect was that having validated that piece on the software side, we started adding these building blocks on the portfolio where in parallel to our software, we were continuing to innovate on the DNA IP. And as I mentioned, the paradigm is this co-design principle. If you're co-designing your software and hardware together, you don't need very large teams. You can do a lot with smaller teams. I'll give you an example. When I was starting, that time, I think one of the earliest examples in the industry on the AI processor side, one of the first companies that at least brought a commercial AI processor was Tesla. And Tesla had an NPU. And Tesla's NPU team was basically 10 people. And I know that in good authority. And I think that energized us. So it is possible, and we are seeing this paradigm shift in the industry. So if you have a very robust software stack, if your tool chain exists, you're working with partners from the very beginning, you're not trying to do everything yourself. And as a company, we are building silicon, but we take ownership of what we call the silicon design. But then we work with our partners on the backend side. We work with leading foundries like TSMC to offload the rest of the process to create a very scalable product and bring that to mass production. That allows us to do a lot with smaller teams. Third aspect, you asked this question about scale. I guess the related question is, how do we achieve a lot of this with a limited amount of funds compared to, let's say, somebody like NVIDIA? And the clear answer to that is, I think, Japan gives us an advantage there as well. Japan has a lot of talent pool. We are now today also seeing a lot of support from the government, which is great, I think. And we are seeing this startup ecosystem developing quite actively. And we have no dearth of talent pool. We are able to attract talent globally. We are in Japan, but we have talent pool, which is across 9 to 10 different countries. And that gives us a operational cost advantage being in Japan, as well as the new center we're creating in India, unlike if you had a purely Silicon Valley company. Those are a few aspects that has allowed us to scale very quickly.
All right. Thank you very much for that. Now we are coming towards the last 5 minutes or so of this session. So again, if anyone has any questions, please put it into the chat box. Sorry, and I'll be happy to bring it up. Now, just on the chiplet thing, I wanted to bring up earlier. It does feel like there is a sea change in suddenly the way the semiconductor industry has been evolving, and of course, the long arc of it was vertically integrated houses, the IDMs, and then we basically essentially disaggregated it. So we had a fabless, and then we have foundry. But actually, we're taking it. Look. In fact, you had a slide that kind of hinted at this. Is we are seeing I would say not fragmentation is not quite the word I was going to go for, but certainly an efflorescence, maybe like Cambrian explosion, right? And it feels like if you look at, like, for instance, Intel's foundry strategy, they're actually embracing this. I mean, the idea that Intel would embrace x86, RISC-V, ARM, and support it, with the tools, with the engineering, with the resources to support a very heterogeneous world seems to be a big change to me. And so when you said, okay, you're entering with a chiplet, that you can actually bolt on your device and add it, to other people's chips. I think this would have been far-fetched to imagine 5 years ago, 10 years ago, 15 years ago, impossible probably about 30 years ago. But today it seems like this is the right time, that we are reaching a world where we can literally plug in and play pieces of silicon of different types from different teams to create the system that you want, the functionality that you desire. And that seems like it's really like a unique time, or just the right time, a perfect time for EC to be founded in 2019.
No, I mean, Damian, I could not have agreed more. Well, of course, I'll qualify it a little bit further. So what we have done with the first platform that you see here on the screen, that's to combine across multiple processors, right? Mixing and matching, let's say, a CPU with EdgeCortix Sakura, or a ARM with EdgeCortix Sakura, or different, Renaissance with EdgeCortix. That we have already validated and done that. The next step for us was the natural transition inside the silicon itself. So rather than being focused on a single SoC, the challenge with an SoC is that it requires at least 2, if not more, years to bring that product to market. And then you have to go and discover the market fit. So you're mixing and matching different IPs. With chiplets, we are now seeing that the industry is moving to a paradigm where if you have a silicon-proven IP, you can make that into a single die and then have that disaggregated, where you can now mix and match different dies. You can separate your IO to be a completely different, that could be different process nodes. So while we can be in 12 or 7 or 6, you can then go and take a IO die that can be at an older or a higher process node. And memory could be a separate die. So from matching different processes, heterogeneity, we are now getting inside the silicon itself while creating a package, system and package that mixes and matches different dies. And really, the time is correct because now at least we have the technologies that can do that. I will say that the caveat today is the dream of chiplets as a complete Lego-like block is still not yet there. It will still take the industry a little bit time. While UCI is going a long way in terms of a standard that allows multiple chiplets to talk together. And we as a company, we are also embracing UCI. But UCI, just like other standards, it goes both ways. So today, as it stands, if EdgeCortix is creating our own chiplet, we need to understand what the other person's chiplet, the language it speaks. So the UCI kind of is a standard that goes both ways. So that will also mean that the way we are envisioning the chiplet industry growing is you will have to know who your partners are. It will not be completely Lego-like where you can mix and match with anybody, but you will have to choose your partners. And within that ecosystem, it will grow a lot more faster. But yeah, absolutely the right time where we are at least able to do that. 10, 20 years ago, you're absolutely right. It was a dream. We have solved quite a lot of the aspects with the software. So we are now looking to scale that up in terms of the heterogeneity on the chiplet side.
Well, it's all very inspiring and very exciting. And certainly I think I can see how, EdgeCortix will certainly contribute to, I think, this grand flowering of like AI in the world, and certainly help Renesas and other semiconductor manufacturers sell more chips. I think, and certainly for yourself to sell more chips too. I think it's a very exciting time for everyone. I'm certainly look forward to what EdgeCortix will accomplish in 2024, and certainly look forward to expansion and further growth of your company. So Sakya, we're up to time right now. So since there are no further questions in the chat box, this recording will be shared, of course, with other investors and other parties interested, and hopefully, we'll get another chance to speak again.
Thanks for the opportunity. It was a pleasure, and I look forward to further such discussions. We as a company, we are still young, but we are definitely punching above our weight class, and we are hoping to contribute actively in the industry. Thank you.
Thank you. All right. Thank you everyone for your time this Friday. You may disconnect from the Zoom room now.